I'll be speaking about sort of a personal mathematical perspective of machine learning. I say mathematical because I'm a mathematician. So machine learning, people have been looking at machine learning from different angles, from theoretical computer science, from statistics, from approximation theory, numerical analysis, from information theory. So my perspective would be more like numerical analysis, computational mathematics, approximation theory. So let's first start with some examples of what machine learning has done. The first example is image classification. So we are given this data set. This is a very well-known data set called CBAR-10. Each that consists of lots of images. Each image is labeled by the content of the image. For example, these are airplanes, these are automobiles, birds, cats, deers, etc., etc. The task is to learn the function which would tell what's contained in each image. So this is a function in very high dimensional space. Each image can be considered as being a point in a 32 by 32 by 3 dimensional space. 32 by 32 because that's the number of pixels. 3 because that's the dimension of the color space. So mathematically, we can think of as being trying to approximate a function f star, which is a mapping. It's a function defined on the 3072 dimensional hypercube cube, and then the function values takes 10 values. So this is one example. The second example, if you look, these are pictures of human face, and these pictures share one thing in common, namely they're all fake. So what's done here is that from real human face, one can learn the probability distribution behind real human face. And then from that probability distribution, we can sample new points, and these two new points are pictures of fake human face. So that's possible because of modern machine learning. So all these examples, are made possible by our ability to accurately approximate high-dimensional functions using a finite piece of data. Now, this opens up new possibilities for attacking problems that suffered from the curse of dimensionality. So curse of dimensionality is a very well-known problem across a very wide range of scientific disciplines, which says that as dimensionality grows, computational cost grows exponentially fast. So that has been a bottleneck for many problems, different problems. So before I give you more examples, let me just give you an outline of the usual deep neural network stochastic gradient descent paradigm for machine learning. So in the supervised learning task, like the first one that I explained, there are 3 components. The first component is that you have to choose a hypothesis space. So that's just a set of functions. We're going to use that set of functions to approximate the target function. For example, this kind of function is called a 2-layer neural network. 2-layer neural network because 2 layers because there are 2 sets of coefficients, 2 sets of parameters that we're going to optimize. And neural network because of this form where sigma here is a nonlinear activation function. It's a scalar function. For example, this is a very popular choice. So we can use these kinds of functions by choosing appropriate parameters. We can use these kind of functions to approximate the target function f star. This is the first component. The second component is to define a optimization problem that we're going to use in order to find optimal parameters. For example, since we're given these data values, we're going to just try to fit these data values with the functions in the hypothesis space. So this is a very natural choice. And this is called empirical risk, can be expressed in this form. So that's the second component. The third component is to optimize this function, choosing an optimization algorithm and the parameters for the optimization algorithm. And this is a very common choice. It's just a gradient descent algorithm. And if you look at this, to calculate the gradient at each step, you need to calculate the sum, and that's expensive. So a very popular choice is to replace the sum by just a sample in the sum. So this version is called stochastic gradient descent. And turns out this version not only saves computational cost, but also very often improves the performance of the whole thing. So these are the major components. Now, given these, so now I'm going to explain some sort of applications in scientific computing or computational science. The first example is a stochastic control problem, and this is probably the one. I think this is the very first example of applying deep learning to problems in scientific computing. Now, this is a standard dynamical system for stochastic control. This is the nonlinear function. AI is the control at step, AL is the control at step L. This is the random noise. We're going to choose these controls to optimize this cost here. This is the terminal cost, this is the running cost. So we're going to look for feedback control. Namely, the control is a function of the state. Now, if the state is high dimension, and this will be a high dimensional function, and this is usually not possible to do in the traditional approach. But now we're going to approximate this by some neural network. Never mind the details of how we do that, but let's think about abstractly. We're going to replace this by a neural network, where theta L is the set of parameters for this particular neural network as time step L. And we're going to choose these parameters to optimize the same computational cost subject to this stochastic dynamical system. This can be done. Again, the details don't matter. I'm going to just show you the flavor of what can be done. And you can see that this is an example of energy storage with multiple devices. The number of devices is 30, 40, 50. And this is sort of the reward as a function of the training steps. You can see there's a nice convergence. The solid line is the mean of the reward, and the shaded area is the variation, the fluctuations of different training when you choose different initial conditions to train the neural network. So this is the first example. The second example is to solve PDEs. So this is a nonlinear parabolic PDE, initial value problem. But oftentimes, it's easier to formulate it as a terminal value problem. So we're going to do this transformation in time and then rewrite this problem in terms of a terminal value problem, where the terminal value is given. So in order to develop deep learning-based algorithm for this particular problem, we're going to first reformulate this PDE problem as a stochastic optimization problem. We're gonna try to formulate this problem as something like this kind of a problem. Okay, to do that, we introduce the backward stochastic differential equations, BSDs, and these are the BSDs. So I claim, and this can be shown rigorously, that this problem is equivalent to this problem, namely we minimize the value of this process y at terminal time t, and the difference between the value of y at terminal time t and the given terminal condition, subject to this BSD as the constraint. Okay. Now the equivalence between this and this is given by this. So y is actually the solution of u at the process x, and the process x is defined by this Ito dynamics. And process Z is defined by sigma transpose grad U. So this is called nonlinear Feynman-Katz formula for the, it gives an alternative formulation of the nonlinear problem. So now, since we'll formulate a problem in this type, and this is exactly the same as this problem, so we're going to use these kind of ideas to develop algorithms for solving this nonlinear PDE. Again, I'm not going to give you the details, but let me give you an example of the kind of results. Consider this stochastic control problem. Go back to the stochastic control problem. M is the control here. This is the winner process. So we want to choose the control to minimize this cost function, terminal cost, and running cost. And this problem, there is a associated Hamilton-Jacobi-Bellman equation, and it's exactly this. Okay, and this Hamilton-Jacobi-Bellman equation can be solved exactly by introducing the so-called Hopf-Koh transformation. So with that, we can write down the solution in this, and this is a solution formula. So we can use this formula to test the algorithm that I proposed earlier. And this is the kind of results. You can see that the two results agrees very well. And we've also developed a platform, open source platform, where we'll put the codes there, and people are, have also put their codes and revised our codes, improved our codes, so that it's easy accessible to a wide community of people. Third example is molecular dynamics. Molecular dynamics is to try to understand a system of a molecule, some molecule or material system by following the dynamic trajectory of all the atoms in that system, in that material or in that molecule. And the dynamic trajectory to satisfy Newton's equation. So what's complicated here is the interaction, the potential that describes the interaction between all the atoms. And that's a complicated stuff because that's got a quantum mechanics origin. Traditionally, there are two ways to do this. One is to calculate on the fly, calculate this force from quantum mechanics models. For example, the very well-known Carl-Peronello molecular dynamics. Both Carl and Peronello are, Italian-born computational physicists. This Carl-Peronello molecular dynamics has made a huge impact in molecular dynamics because it made molecular dynamics really trustworthy. Because this is because this is the first time where molecular dynamics is accurate. Okay, so this is accurate, but it's also expensive. It's limited to about 1,000 atoms. Even with very high performance computers. The other way of doing it is just to guess what this V is. Now, this is a very hard task because V is a complicated function, describes a very complicated interaction. But people just try to guess. And so this is not reliable. So now we have a third paradigm, which is to just use quantum mechanics models to supply the data and use machine learning to train a neural network model and then just plug the neural network model in here. And this runs with, as almost as efficient as empirical potential. Okay, so this is the new paradigm and it has been worked out. And this is one of the examples. You can see the accuracy of these machine learning models for a whole wide range of systems, ranging from small molecules. This is the aspirin, this is the ethanol, these are other molecules, and to large molecules. This is a parity, this is a big, huge molecule, to different kinds of surface materials, metals, oxides, and this is a very complicated high entropy alloy with 5 components. So across a very wide range of different systems, this kind of methodology works very well, accurate, very accurate, as accurate as your quantum mechanics model. And with this kind of a model, one can speed up molecular dynamics. So this is we call deep MD, deep potential molecular dynamics. So we'll implement deep MD on Summit, which is the second fastest computer in the world. And we can now handle systems with 100 million copper atoms. That's the speed up of 5 orders of magnitude, and 4 millions of water molecules. So these are the kind of things that were not possible before. And again, we've developed open source platform with different codes, and people are using this open source platform to develop their own applications. I just want to mention this briefly. This is an example of protein folding, and we're able to do protein folding with nonlinear multigrid method. So multigrid method is very popular in computational mathematics, but to apply this kind of ideas to a very nonlinear problem like protein folding has been a very tough task. I've thought about this for more than 20 years. And now with the help of machine learning, we're able to do this. So I'm not going to explain the details. I actually have a paper, a review article written along the lines of what talk I'm giving here today, and it's available on my webpage. So if you want to look at some of the details, you can go there. And this is my last example. It's we all know that Euler equation works very well for gas dynamics. But when the Newton number is big, Newton number is a very important parameter for gases. It measures the ratio between the mean free path and the size of the system. So that's the epsilon here. So this is the Boltzmann equation for gas dynamics. So if epsilon is small, this Boltzmann equation can be approximated accurately by Euler's equation. But if epsilon is large, that's no longer the case. So the question has always been, can we extend Euler's equation to include more moments of the Boltzmann equation and obtain a system that can describe gas dynamics over a wide range of Newton numbers? So we've developed something like this using machine learning, and this is the result. This is some examples of the result. So here I'm only showing results for different Mach numbers. This model is also uniformly accurate for different range of Newton number epsilon. So you can see that, you know, for different Mach numbers, there's very good agreement between the blue line and the green line, which are the results of the Boltzmann equation and the machine learning based learning moment closure. The orange line is Navier-Stokes. You can see there's quite a departure. So this is a typical multi-scale problem where epsilon describes sort of the difference of the scale, molecular scale, and the macroscopic scale. And these kinds of multi-scale modeling problems have been around for a long time, and we were not able to attack them. And I spent a lot of time over my career to think about these problems. And indeed, there are many more problems of this type. So this is the hierarchy of physical models. All the important physical models, going, you know, from Schrödinger equation, quantum mechanics, all the way to Navier-Stokes equation, elasticity, continuum mechanics, turbulence models, and, you know, Boltzmann equation, and then coarse-grained molecular dynamics, density functional theory. This is the hierarchy of physical models, and integrating these different physical models, which together has been the ultimate objective of multi-scale modeling. And it was very difficult 10 years ago. So now with the help of machine learning, you know, machine learning has given us new hope. It seems like machine learning has been the missing tool in order to realize the dream of multi-scale modeling. Okay, so lots of other things that progress has been made, developing machine learning-based algorithms for computational science, scientific computing. Again, I'm going to skip them. So what I want to do, spend more time on, is some sort of mathematical question. Understanding mystery about the machine learning. So there are two key questions. The first question is, why does it work in such high dimension? The second question is, why is it so fragile? Machine learning requires extensive parameter tuning. So why is that the case? I would say these are the two most important questions, mysteries about machine learning. And then the second question is, can we formulate better machine learning models, more robust? Okay, so let me address this, try to address these two issues. Certainly, there are lots of questions that we don't understand, but I want to give you an idea of what we do understand. So I'm going to start with approximation theory. Classical approximation theory, we approximate functions by polynomials or piecewise polynomials. And we have this kind of error estimates, where m is the number of free parameters in the model. H is the sort of grid size. No, let's think about piecewise polynomials. So H would be the grid size over which we define the piecewise polynomial. So H is related to M by this expression, where D is the dimensionality here, the dimension of the problem. So this kind of error estimates is a typical classical result. Two things that are important. First of all, the error constant that controls the error constant that depends on the target function is defined by the Sobolev norm, namely defined by the smoothness, regularity of the function. So this is the typical situation in classical approximation theory. Secondly, if you look at this first factor here, because of this 1 over d in exponent, this is a sign for cursive dimensionality. For example, let's take alpha to be 1. Then, in order to reduce this factor by a factor of 10, you have to increase m by a factor of 10 to the d. Okay, so if d is 3000, that's a huge number. So that's cursive dimensionality. Now, in high dimensions, there's one example in high dimensions that has been worked out very nicely, and that's the example of calculated integrals. So if you want to calculate this expectation, which is just an integral, where mu is some probability distribution, you can do it the following way. You take an ID sample of mu, and then you replace this integral by this empirical sum. The error between this, in this approximation, Monte Carlo approximation, can be computed exactly, and it's the variance of G, defined this way, divided by M. Notice that there's no 1 over d in exponent. So this is great news. This means that the convergence rate is independent of dimension. Secondly, the error constant, what plays the role of this thing here, is the variance of G. So the best we can hope for, or what we're looking for, is something similar in the context of functional approximation. Here it's just calculate integrals. We face the harder task, which is that we want to approximate functions in high dimension. So we want to have something like this, where the error is bounded by something like 1 over m, and then something which plays the role of the variance, which I've written formally as some sort of a norm. Not necessarily a norm, but I wrote formally as some sort of a norm. So that's what we want to achieve. So can we do this? Can we do this? Is that possible? Or how can that be possible? So let me give you some intuition right here. Take this expression. So this expression is nothing but expressing a function f by its Fourier transform. Okay, classically, we've been trying to approximate something like this by fast Fourier transform. Namely, we discretize this on a uniform grid. Okay, then we get this. The error between the two is given by this formula, where alpha is like the degree of smoothness of f, the number of derivatives. You see this here. So this kind of approximation suffers from recursive dimensionality. That's why Fourier methods, spectral methods, don't work in very, very high dimension. Works very well in low dimension, but if you talk about 1000 dimension, it doesn't work. So this is the classical approach. But now, imagine we're going to replace this representation of the function by this representation. The only change here is that we replace d omega by pi d omega, where pi is a probability distribution. In this case, this function f can be written as an expectation. Then it's very natural to approximate this by Monte Carlo. With the Monte Carlo, the error rate is this, as we saw before. Notice that this approximation can be expressed as a 2-layer neural network, where we just write this as AJ, and we take sigma to be a nonlinear activation function defined by e to the ID. So this is the 2-layer neural network. So what I'm saying here is that if you have a function that can be expressed in this form, that kind of a function can be approximated by a 2-layer neural network with an error rate that's not that's independent of dimension. Okay, so there's key difference between these two expressions. So now with that background, let's look at approximation theory for two-layer neural networks. So again, this is the general expression for two-layer neural networks. The parameters are AJ and WJ. So I'm going to take sigma to be this particular nonlinear function called ReLU nonlinear function. So first, we're going to define the analog of Sobolev space for this approximation scheme. In order to do that, we're going to need to restrict our attention to functions f, which admits this kind of a representation. So this representation is nothing but the continuous form of this, if you think about it, where rho is the probability distribution. So again, if you have a function with this form, that function can be expressed as an expectation. Okay, so for these kinds of functions, we're going to define a norm, which we call Barron norm, in order to honor Andrew Barron, who has made a lot of contributions to this. Now, notice that Barron also defined his own norm. It's different from this. Okay, so this is what we call Barron norm, and it seems to be accepted terminology in machine learning literature. It's different from the norm Barron himself defined. It's a bit confusing. But anyway, we're going to define this norm as the Barron norm. And if a function, for functions whose Barron norm is finite, we call them Barron functions. So why we define this particular norm? Well, it's because with that norm, we're going to do approximation theory. But first of all, before I go further, let me just mention that the following result. Namely, it's natural to ask, the natural question is, what kind of functions are Barron functions? What kind of functions admit this representation? The answer is given by a theorem proved a few years ago by Barron and Klosowski. They show that if a function has fast decaying Fourier transform, such that this integral is finite, then f can be f has a representation of this form, and the Barron norm of f is bounded by this particular quantity, which is the norm Barron defined. Okay, so this result, gives us some idea about what kind of functions in Barron space, but this is not satisfactory because this condition is a dimension dependent. So this in order for this to be true, the decay condition on f hat is dimension dependent. Okay, so it's still a good question, a very important question to ask. What kind of functions are Barron functions? Let me give you some examples. So the L2 norm of a function is a Barron function, but the distance to a sphere is not a Barron function. So these kind of results, you can find these kind of results from this paper. Characterize the kind of functions. Okay, so the reason we define Barron function is really here. Namely, with that kind of a definition, we can prove direct and approximate and inverse approximation theorem. Namely, if a function has finite Barron norm, then that function can be approximated by a two-layer neural network with this kind of Monte Carlo rate, where the error constant is given by the Barron norm. Conversely, if a function f star can be approximated by two-layer neural networks with some uniform bounds, then that function f star has to be in the Barron space. Namely, it has to have a representation of this type with some probability distribution rho star, and the Barron norm is finite. Okay, so that's the first issue, namely the approximation property. The second issue is the following. We're only given a finite piece of data, training data. Is it possible that we get a machine learning model that works extremely well on the training data, but doesn't work at all away from the training data? So that's a natural question too. And indeed that can happen. And this is the classical illustration of the classical wrong phenomena called wrong phenomena. And here, what's shown here is polynomial approximation on an equidistant grid for a very nice function. So this function is given by this blue line. But the polynomial approximation, polynomial interpolation is given by the red line. On the grid points, they agree exactly because that's interpolation. But away from the grid point, you can see there's a big, huge deviation from it. So these kinds of models we don't like, we don't want, because they don't work well away from the training data set. The way in order to measure the difference between the training accuracy or training error, this kind of a training error or testing error. So this is you also call it empirical risk. This is also called population risk. In order to measure the difference between these two quantities, very important quantities. One tells how it performs on training data. One tells how the model performs away from training data, the typical data. So in order to control the difference between the two, in machine learning, there's an important notion called Rademacher complexity. And that's the one quantity that controls the difference between the two. Basically, the supremum of the difference is bounded by above and below by Rademacher complexity. And Rademacher complexity measures the quality of the approximation of how functions in the hypothesis space can approximate random noise. So given a hypothesis space, H, let's try to pick up functions from the hypothesis space to fit random noise psi I. So these are just IID random variables that takes +1, -1 values with equal probability. So if the function can fit noise very well, that means the set of functions is very complicated. That means the Rademacher complexity is big. That means this difference can be very big. But so we want hypothesis spaces with a small Rademacher complexity. Now for Barron function, for the if you take a unit ball in the Barron space, the Rademacher complexity is bounded by 1/√n, essentially bounded by 1/√n. Now, in contrast, if you take a unit ball in Lipschitz space, then this would not be 1/√n. This would be 1/n to the minus n to the 1/d. So there it would be an exponent of 1/d. So that means that the Lipschitz space is very big. The Rademacher complex is very big. And if you want to fit functions with the Lipschitz functions, you would require a lot of data. So combining these two, these two kinds of results for approximation error, results for estimation error, we arrive at the following kind of a priori estimates. If we consider this regularized model, so we take the empirical risk regularized by the really the Barron norm for the neural network function, then one can show that every global minimizer of this regularized model satisfies this kind of a result, namely with high probability. So for any delta with probability 1/delta, this is true, that the population risk or the test error is bounded by something like 1/m and something like 1/√n with coefficients that defined by the Barron norm. Up to some not important logarithmic factors. Okay, so these kind of results have been proved not just for two-layer neural networks. I was only discussing two-layer neural networks, but also for random feature models, random residual neural networks, ResNets, and multi-layer neural network models. And the result is that we have this kind of error estimates up to logarithmic terms. Okay. So these are the most popular neural network models. So next time we're going to look at machine learning from a continuous viewpoint. And the reason being that this we hope that this continuous viewpoint will be sort of more intrinsic formulation of machine learning. Okay, so in order to do that, the first thing we need is how to represent functions. Okay, so this is the one way to represent function. We have seen this before. Okay, to represent a function by this kind of expectation. So we have seen this before. And we can generalize a little bit to define more general features. Instead of this kind of a special form, we can write down some more general functions of two variables where u is the feature vector. So this is one kind of representation. We call this integral transform-based representation. Another kind of representation, which is that we represent functions by from the result of a nonlinear dynamical system. So let's consider this kind of a dynamical system. The flow map at time 1 would be this function, and this is generally a nonlinear mapping. And we just add all the components up, we get a scalar function. So G, this right-hand side G, one possible choice of G is to use this idea here, to choose G based on this form, this kind of representation. So if you look at this seems like come out of the blue, but we'll see later that it's actually, this is actually very natural, arises very naturally. Anyway, so suppose we now have represented the functions by this expression or this kind of expression, and then the parameters are the probability distribution rho. Here, the parameters are these one family of probability distribution rho tau. So we're going to use these, we're going to choose these parameters in order to minimize the population risk, which is this quantity. That's the definition of population risk. The question is, how do we define gradient flow dynamics to minimize this population risk? Here we draw some ideas from inspiration from statistical physics. Namely, we view this as free energy, and we view these parameters as either conservative parameters or non-conservative parameters. For example, if we have an expression of this type, and the parameters, both a and pi are parameters, pi is a conservative parameter because the total integral of pi has to be 1. It's a probability distribution. A is a non-conservative parameter. It doesn't have this constraint. For non-conservative parameters, we can define gradient flow by this straightforward so-called model A dynamics. But for non-conservative order parameters, the probability distribution, we define gradient flow differently. We first define this thing called chemical potential, and then we define velocity from the negative gradient of the chemical potential. That's called Fick's law in physics. Then we define the current, and then we have the continuity equation. So this is how we define gradient flow for probability distributions. And this is also gradient flow of this free energy under the Wasserstein metric. Anyway, so now the machine learning problem is reduced to solving these kind of PDE. Now this is like a PDE. So how do we solve this PDE? Well, we need to discretize. So how do we discretize? The first step is to discretize the population risk into empirical risk, and that's easy. That's just using data. The second step is to discretize the PDE, the gradient flow. So we can use particle method, and in high dimension, particle method is the method of choice because that's the analog of Monte Carlo. If we are working in low dimension, we can also use a spectral method. We don't even have to use particle method. And there's also an improved version of particle method called smooth particle method. And that in numerical analysis, it has been shown that smooth particle method works better than particle method. So let's see how things work, once we discretize using these algorithms. So let me give you an example. Let's look at this representation. Okay, so the gradient flow in this case is defined in the following way. Okay, and we want to discretize this PD-like thing using particle method. Well, that means we'd replace the probability distribution rho by this empirical sum, and where these are the particle, the position of the particle at that time t. You can write this in this way. So now I claim, so here one can prove a little lemma that says the following, namely, if we define the following dynamical system for the particles uj, where the function I is defined by the population risk, limited to a function m, given the following form. So if you evaluate the population risk at fm, since the variables are these uj's, we get a function which are the functions of the uj's. If you look at the gradient flow for this function, I claim that gradient flow is equivalent to this PDE. Okay, so that's so that shows what? That shows that this is nothing but the gradient flow for two-layer neural networks. So this little lemma that I didn't write explicitly, but I just outlined, says that this PDE, the particle discretization of this PDE is exactly the gradient flow dynamics for two-layer neural networks. Now, okay, except there's a little the following. Here, notice that the two-layer neural networks that I described here has this factor 1 over m. But in the usual machine learning literature, this factor 1 over m is not there. If you look at and this makes a huge difference when it comes to gradient descent training. So here's an illustration. Just consider if we take the so-called conventional scaling without 1 over m and train the model with gradient descent, we get this result. And this is the test error, the heat map of the test error as a function of the logarithm of n. N is the size of the data set, and logarithm of m is the number of neurons. You can see on this heat map, there's a phase transition between a good phase and a bad phase. If you pick a parameter, if you pick your neural network parameter, you pick m in this phase, you get big error. You have to pick a parameter, the value of m, so that you're in this phase. And this is just two-layer neural networks. If you have multi-layer neural networks, the phase diagram would be more complicated, and the task of choosing the right parameter would be even harder. But if you look at this scaling, there's a 1 over m here. You can see that the error is smooth. There's no phase transition. So this little result suggests that if you follow the continuous paradigm, we do the continuous paradigm, then this is discretized, like going through this. We get more robust models. The performance will be more robust. By the way, in this particular setting, the equations that I wrote down here, this equation is the same as the so-called mean field equation for two-layer neural networks. And so this is 2 years ago, there were several papers, independent work, that look at the mean field limit of two-layer neural networks. And in the limit, they recover this equation. Here, what I'm saying is that if you just follow the usual physics recipe, you would get this equation right away. Okay, now if we look at the so here, this is just two-layer neural. This is just sorry. This is looking at representation of this type. So now let's consider representations of this type, which we call flow-based representation, which means we first look at the dynamical system dz d tau is equal to this, and then we choose the optimal parameters here with this one parameter family of probability distribution rho to minimize the population risk. So let's look at this problem. So this is, again, it's a dynamical system. And we view rho tau as the control at time tau. So rho is the probability distribution. And we choose these parameters to minimize the population risk. So this is an optimal control problem. For these kinds of optimal control problem, there is a maximum principle. Contraction is the maximum principle. To state contraction is the maximum principle, is defined as Hamiltonian. This Hamiltonian, then the contraction maximum principle claims that the optimal parameter at each time tau, at each solo time tau, is the maximizer of this expected Hamiltonian, where Z and P are the states and co-states defined by the forward and backward equation with this kind of a boundary condition. So this is the contraction maximum principle formulated in this particular context. Now, in typical machine learning, people use gradient descent. So we all know that people use gradient descent. So so the natural question is how to write down gradient descent dynamics. And then it's easy. It's just replace this argmax principle by gradient flow. So this will be the gradient flow. So this formulation here, the only change is that it would replace the argmax condition by this gradient descent dynamics. So this will be a continuous formulation based on flow for the flow-based models. Now, if you discretize this, so we discretize by taking forward Euler for the dynamics for the dynamical system, and particle method for this gradient descent dynamics, then we recover this thing. We get this numerical algorithm, and this numerical algorithm is nothing but the gradient descent algorithm for these ResNet, residual networks. Okay, so this says that the very natural particle method discretization of this continuous formulation recovers gradient descent algorithm for ResNet, residual neural networks, which is the most popular network. But you can just, you don't have to take this discretization. You can just take smooth particle method. You can do spectral method. You can do other things. You don't have to do forward Euler. You can do other things. And then you can get other machine learning models and machine learning algorithms. So on the other hand, we can also go back to the maximum principle and formulate numerical algorithms based on this maximum principle. And this is done here by Chen Xiaoli, my former student Chen Xiaoli. And this is just straightforward discretization over the maximum principle. And turned out it doesn't work so well. And it works much better if we extend the maximum principle into some sort of extended phase space, define extra auxiliary variables V and Q this way. Okay, no, this extended so-called method of a successful approximation, which is just the maximum principle. This extended version works out very well compared with the standard gradient descent algorithms used in machine learning. For example, this is a comparison. The green line is the maximum principle, the extended maximum principle, and these other lines are the stochastic gradient descent algorithms. And you can see, green line always outperforms the stochastic gradient algorithms. And this is the situation where you tune your initial condition nicely. This is the situation where you don't do that. Just pick some bad initialization and then see what happens. In that case, the improvement is even more drastic. So let me conclude, and with the question of what have we really learned from machine learning? So machine learning has a whole bunch of tricks: gradient descent, stochastic gradient descent, dropout, batch normalization, all kinds of tricks. But what is the most essential thing that we have learned? So I would say the most essential thing is these things, that we express functions as some form of expectations, either this one or this one. This is what I call integral transform based. This is what I call flow based. So these, this corresponds to two-layer neural network model. This corresponds to ResNets. Now for multi-layers, we have something else, and this is more complicated, so I'm not going to get into it. And these are really the most essential part. If you can think of another way to represent functions as expectations, that can be the starting point for a whole new class of machine learning models. And based on that, we can then discretize using either particle method, spectral method, or any other numerical methods. And then we will get some sort of machine learning algorithm. And that, I think, is the most fundamental aspect of machine learning. Now, so on my webpage, there are a whole bunch of review articles. This is a review article about mathematical theory. This is a review article about solving high-dimensional PDs. This is a review article about developing multi-scale modeling, real physical models with machine learning. So if you're interested in some of the details, you can look at these review articles. Now, I know my talk has been very sketchy. I wanted to give you an overview of what machine learning has done, can do for problems in scientific computing and computational science, other than computer vision, natural language processing, these kinds of more traditional AI kind of applications. So that's one thing I wanted to do. The second thing I wanted to do is to give you a flavor of the mathematical issues that arise in trying to understand machine learning better or developing better machine learning models. Okay, so my approach has been numerical analysis. It's not about statistics, not about information theory, not about theory of computer science, but rather numerical analysis. And it's really high dimensional analysis, approximating functions. I didn't talk about it, but if you look at other machine learning tasks like unsupervised learning, generative models, or reinforcement learning, you would get into other mathematical issues like solving PDEs in high dimensions or approximating probability distribution in high dimensions. So anyway, the heart of mathematical theory of machine learning is really high dimensional analysis. So with this, I should finish. Thank you very much for your attention.